Okay, a very good morning to all of you. I am sharing the QR code with you all. So kindly give the attendance first and then we will start. Why people join so late? Huh? Okay. Give the attendance fast and then we will start. You have given your attendance, everyone. So now I can start. Okay. So what I discussed yesterday in my previous class, sensitivity of galvanometer using Wheatstone bridge. So here you can see a combination or application of Thevenin equivalent circuit. Okay, so I have also discussed the specific formulas for Thevenin equivalent circuit, and we have seen that VTH is some this kind of formula it is coming. Okay, so what you need to find out here in this particular topic, first is VTH, and then you have to find out RTH, then IG. Okay, so RTH formula is this. So I hope you all are much aware of Thevenin theorem. Only that theorem we had applied here. So this thing I have discussed in yesterday's class. Okay, and when you are getting all the combination of resistance to RTH, then what we need a complete circuit that is having a resistance and supply. Okay, so this kind of circuitry actually requires supply is VTH, here RTH is resistance, and two terminals C and D. C and D, that is the input and the output thing which you can see here. And what is our galvanometer current? Current galvanometer current is here will be obviously VTH upon RTH upon plus RG. So VTH is Thevenin voltage, RTH is Thevenin resistance, and RG is Thevenin galvanometer resistance. So as I've discussed these formulas and all in previous class, today we will do some problems. Okay, some problems on this this particular topic. So once a moment, let me share my whiteboard and let me give you the problem. Take it down, the problem. Wait. Yes. Yes. So I'm giving you a figure. Okay. I'm showing you a figure. You have to just figure it out, applying those particular specific formulas. So the figure is just like this. There is a supply of 5 volts. Okay. This is a 5 volt supply. And just draw this figure first. Then I'll give you the statement. Here's a resistance. Okay. And in the middle, you will be having a galvanometer, that is G, galvanometer. Okay. And the naming what I'm doing, you will do exactly like that. And here is a terminal, and this is the B terminal. This is C terminal. This is D terminal. Okay. This much is clear. And this is R1. This is R2. Then you can take it here. This is R3. And this is R4. Okay. So these are the 4 resistances you can see. Now, the question that you will take down, write down, in the figure of a Wheatstone bridge, the battery voltage is 5 volt. In the figure of the Wheatstone bridge, the battery voltage is 5 volt. Okay. And its internal resistance is negligible. So we have to consider the internal resistance negligible. Okay. Then you take down, the galvanometer has a current sensitivity of 10 mm. This is the current sensitivity value I'm writing per microampere. This is mu, actually mu. So the current sensitivity of galvanometer is this one, and an internal resistance is of 100 ohm. Okay, internal resistances are 100 ohm. Calculate the deflection of the galvanometer caused by 5 ohm unbalanced in the arm BC. So you have to find the galvanometer, the deflection of galvanometer, the deflection of galvanometer that is caused by 5 ohm unbalanced arm, okay, BC. Look into the arm BC that you have to consider. Okay. Now you just do the problem and tell me. Oh, one more thing, I need to give you the resistances also that you take down. First, R1, it is 100 ohm, keep it 100 ohm. Okay. R2 you take down 1000. R2 you take down 1000 ohm. And then R3 you take down, R3 200 ohm. Okay, 200 ohm. And R4 you take down, 2005 ohm. Just like this. These are the 4 values of resistance that I have given in your problem, and you're also given the current sensitivity and internal resistance of 100 ohm. So you have to find out. So the bridge circuit is in small unbalanced condition, right? Since the value of resistance in arm BC is 2005 ohm. So what I told you, calculate the deflection of galvanometer caused by 5 ohm unbalanced in the arm BC. But already I have given you that in the arm BC resistances, this is the arm BC. This one is the arm BC. This is the arm BC. Your resistance is already 2005 ohm. So do the calculation first. You find out VTH. How you will find out VTH? How you will find Thevenin voltage? Can anyone tell me? How you will find out Thevenin voltage and what the formula we can apply here for VTH? Tell me that thing. How we can?
VTH is equal
Yes,
to VAD minus VAC.
Very good. VAC minus VAC. VAD minus VAC. Very good. VAD minus VAC. So this is the formula we can apply to find out the Thevenin voltage. So just put the values, all the values you know, put the values and tell me the answer. So अगर हम VAD consider करते हैं, then what is the formula we can write here? R1, what is the formula? R1 upon R1 plus R3. Clear? So the formula we can write, and we have 5 volt already our supply. So that we will keep outside. So I'm going to the next page. Okay. Okay, no. Let me keep into this page only. Otherwise, you won't be able to understand. The 5 volt को हम बाहर रखेंगे. And inside, first of all, you have to write R1. Our R1 is 100. I can see. So 100 divided by means R1 upon R1 plus R3. Okay. So what is my R3? 200. So it is 100 plus 200. Okay, like this, you will also find out VAC. So tell me what is the value of VAC? It will be R2 upon what? R2 plus R4. Okay, so take the values and tell me the result. And tell me the result here. Tell me the result. Done the calculation part. Josna, Monica, yes.
277.
Yes, very good. 277 millivolt. It will be somehow 2.77 millivolt. Okay, 2.77 MV. So this is the value we are getting the of VTH, Thevenin voltage. Okay. Now I need to find out RTH. मुझे निकालना है RTH. So how I will do that? Okay, let me do it here only because next page जाएंगे तो I won't be able to see the picture. Okay. Okay, now I need to find out RTH. So now I have the VTH. I need to find out RTH. So what is the formula of RTH we have? We have to see which resistances are parallel to each other. So what I can see in my figure, R1, R3 are parallel, and here R2, R4 is parallel. So what you have to do? R1 parallel to R3, okay, plus what? Plus R2 parallel to R4. So you know the formula of parallel. So just put it down and tell me the answer. Put the values, and parallel means you know what formula we have to apply. Then put the values and tell me the answer. Tell me the answer of RTH. Tell me the answer of RTH.
734 ohm.
734 ohm. बाकी सब कर रहे हो ना? Only एक ही आंसर दे रहा है. Josna, Monica, Pooja, are you all doing? Avinash, Vinod, today Vinod is there in the class. 734, RTH is 734. Now what you have to find out, you know what is VTH, you know what is RTH, and in the problem, I have already given you the resistance also. The galvanometer resistance I have given 100 ohm. Okay. So how you can easily now find out the IG. IG means the galvanometer current. So I'm going to the next page and I'm writing the formula for IG. So IG you can find out now easily. What it will be? It will be VTH, okay, divided by RTH, okay, RTH plus RG. So this is my formula. Now you know the value of VTH, you know the value of RTH, you know the value of RG. Put the values and tell me the answer in microampere. Okay, tell me the answer. What answer you can have in place of IG? So finally, we are writing the formula, but we should also concentrate on what will be our circuit looks like. So जब मुझे RTH पता है, I know my VTH, the circuit will look like very simple. You know the VTH, okay? You will just draw the circuit like this. I mean, that complicated circuit now will become very simple, okay? You will have a galvanometer here, and this is the circuit. So here I know what is my RTH, okay? You know what is your VTH, so you will put the values here. And in galvanometer here, you know what is you have to find out what is the IG that you will find out now. And you already know what is the resistance of galvanometer here, that is 100 ohm, okay? So you place the values here. This is the circuit, ultimate circuit we are getting. So tell me the answer. इतना टाइम क्यों लग रहा है? Tell me the answer. Hello, Pooja. Pooja is there?
Yes,
Pooja,
ma'am.
tell me the answer. ये करने में इतना टाइम क्यों लग रहा है? Just put the values and tell me the answer.
Ma'am, I didn't heard properly.
Didn't hear properly. इतने टाइम से बोल रही हूँ. हाँ, आयुषी, tell me the answer.
Ma'am, 3.32.
3.32, very good. 3.32 microampere somehow. Now you have to find out the galvanometer deflection. What it will be? Small d. Okay. Deflection, that will be, you see here in the problem, I have given the current sensitivity of 10 millimeter. So that you have to just multiply here. That means 3.32, okay, 3.32 microampere multiplied by 10 mm, 10 mm per microampere. Okay. So इसको अगर पुट करोगे तो तुम्हारा वैल्यू आ जाएगा 3.32 mm. So this is my deflection. So this will be my answer. Okay. This is the galvanometer deflection that you are getting out of this problem, and above, and after applying Thevenin theorem. Okay. So I think you've understood this kind of problem will come in your exam. Yes, Etasam, anything you want to say? Etasam?
मैम वहाँ पे 33.2 होगा ना?
33.2. 30 कहाँ पे डिफ्लेक्शन में?
10 into 10 है मैम.
yes, sorry, एक मिनट. यहाँ पे 33.2 mm होगा. 33.2 mm होगा. Sorry. ठीक है? This is my deflection and I'm getting. This is the answer. Okay. So very important, this kind of problems will come in your exam. भले objective type questions हो, तो ऐसे problems आएंगे. ठीक है? Then you have to just apply your formulas and you can simply do it. Okay, I'm sharing again my presentation where I left out. So this is the problem which we did just right now. Another problem is there that I will give you in the homework. Now let us come to some of the applications of Wheatstone bridge, though it is not so much in your syllabus, but just try to keep in your mind where Wheatstone bridge is applied. This is important. So first is Murray-Worley loop short circuit loop test. Okay, this is one of the loop tests where we can use Wheatstone bridge, and this kind of test can be carried out for the location of either ground or a short circuit fault. So you see in some of the transmission lines, you can see here na, two poles are given, and here many long power lines are connected, and so you can see here when during long transmission time, this kind of some short circuit fault may occur in the wires, okay, in the transmission lines or power lines. So there, to detect the fault, sometimes we use Wheatstone bridge as a good device to understand the for doing the Murray loop test. So the word is Murray loop test. So you just remember that we can apply Wheatstone bridge in Murray loop test for identifying the short circuit fault in long transmission line. Okay, and here they have shown in my PPT, I have shown here that how the circuit of Murray loop test looks like. So you don't have to do so much. Just remember that Wheatstone bridge can be applied in Murray loop short circuit test, where long transmission lines, some short circuit fault may occur. Okay, so this much will help you, nothing more. So here are some in my PPT because when I read Murray loop test, I had Murray loop test in my syllabus. Okay, so you don't have to do that much because it's not in your syllabus. Okay, now application of Wheatstone bridge. Another thing, let me tell you, that is, see, in Wheatstone bridge we have two types of things. Okay, unbalanced and balanced. So in any problems you are getting, you should check whether it's a balanced problem or unbalanced problem. Same here again in unbalanced bridge, they have taken that that the unbalanced, which means what? Any of the resistance will be having a different value from the other resistance. Okay, that is unbalanced thing. If all the resistance have the same value, then we can say that's a balanced bridge. Okay, so see this kind of the last paragraph written here. This kind, this kind of bridge can be found in sensor applications. The resistance in one arm is sensitive to the physical quantities such as pressure, temperature, and strain. So this you have to check out that where we can have unbalanced bridge. Okay, so an unbalanced bridge also somewhere Wheatstone bridge is a good application. So then about Thevenin and Thevenin resistance and Thevenin voltage, already you know, you are much aware what is the value. So here is some problems regarding this unbalanced breach. Okay, so we will do these problems, but I will give 2 or 3 assignments also. Now, Wheatstone bridge, we have more or less covered doing the problems, error, sensitivity, and everything. Now, one more important thing is that after Wheatstone bridge, we are having Kelvin double bridge. Okay. Now, a question may come in your mind that Wheatstone bridge definitely has some limitations in their sensitivity in deflection galvanometer, and that is why um, we are moving towards Kelvin double bridge. Okay, so Kelvin double bridge there is, it can compensate those limitations of Wheatstone bridge. Using Kelvin double bridge, we can measure low resistances. It's a low resistance bridge. So wait, so let me move on to Kelvin double bridge. Wait. Yes. So there, see in my PPT, it's clearly written that low resistance bridge. So we have to see that resistance must be less than 1 ohm. Okay, so whatever resistance we need to calculate here, in case of Kelvin double bridge, we need to see that resistance must be less than, or you can say it must be small value or less than 1 ohm. Okay, so effects of the connecting leads and effect of the connecting leads and connecting terminals are prominent when the value of Rs decreases to the few ohms. So effect of connecting leads. See, here they have shown a particular structure, circuit diagram to that how in Kelvin double bridge we can draw the circuit. So you can see here R1, R2, R3, Rx is the unknown resistance, and they have taken 3 points. See here in the particular circuit, you can see they have taken 3 points. Let me enlarge the PPT, then you will be able to understand. See here, we have taken 3 points. Why they have taken these 3 points? M, P, N. Okay. And Ry, they have, and this total thing they have taken as Ry. And Ry is the resistance of the connecting lead from R3 to Rx. So R3 is here and Rx is here. So in between R3 and Rx, Ry is existing. Now at point M, Ry is added to unknown Rx, resulting in too high an indication of Rx, and at point N, Ry is added to R3, therefore measurement of Rx. Now let me tell you before going into these things, what is Kelvin double bridge? Okay, that we should discuss first and then we will come to the circuit. So Kelvin double bridge, first of all, I told you if the value of unknown resistance must be less than 1 ohm. So definitely like Wheatstone bridge, it will be again having 3 arms. Okay, and as I told you, it's a DC bridge. Okay, it's a DC bridge, and a Kelvin double bridge is a modified version of Wheatstone bridge. Okay, so it's very common. It's a modified. That is why after Wheatstone bridge we are learning Kelvin double bridge, because it's a modified version of Wheatstone bridge. Okay, which can measure the resistance below 1 ohm with high accuracy. And mind it, here in Wheatstone bridge, we get a very high accuracy. Okay, it is named because it uses another set of ratio arms, such as galvanometer, to measure the unknown resistance value. Okay, and the basic operation of a Kelvin double bridge can be understood from the basic construction and operation of Kelvin. Now let us come to the principle of Kelvin double bridge. Now a Wheatstone bridge is used to measure resistance equal. If I told about Wheatstone bridge, what is the range of Wheatstone bridge? Can anyone tell me? It is greater than or equal to 1 ohm, right? Greater than or equal to 1 ohm. But if we want to measure the resistance below 1 ohm, then we will go with this Kelvin bridge. Okay. So it becomes difficult because leads which are connected to the galvanometer, they add up the resistance of the device actually along with the resistance, leading to the variation of a measurement in the actual value of resistance. So hence, in order to overcome the problem, in case of Wheatstone bridge, we are now opting for Kelvin bridge. Now, as I told you, come to the particular circuit. Let me move on to here. Wait. in this circuit, you just see. So the Kelvin bridge is of resistance R, okay? Kelvin bridge having resistance small r, suppose, and it has to, it connects with the capital R unknown resistance, and that means Kelvin double bridge. If I say, let me share with you my whiteboard, then I can make you more easily understand. Suppose I'm telling you that the Kelvin bridge is of resistance small r, okay, which connects capital R, that is unknown resistance, to standard resistor S. So, according to me, my circuit will be whatever I told you. It will be, I'm drawing as per what I'm telling you, okay. So this is P, this is Q, this is capital R, this is capital S, okay. And here you will be having a galvanometer, that is G, and it is connected to some places like this, okay. And there are terminals called A. This will be connected with a battery or with a supply, whatever. So this is A, this is a small A point, and this is somewhere we can put here A, B point, okay. So now look into this particular circuit where I told that the Kelvin bridge is of resistance small r, with, which connects capital R, this is my unknown resistance, okay, to a standard resistor S. This is my standard resistor S. So resistance value can be viewed in the galvanometer from M to N. How? Now I will connect here two lines I'll take like this. So this point is my M and this point is my N, okay? So the resistance value can be viewed in the galvanometer from M to N. So now I will check from up to this region from M to N. Okay, so this is my supply. Now you see, it means the resistance value is less, and if the pointer shows N, means resistance value is high. So if the pointer shows M, the value of resistance will be less, and if the pointer shows N, then the resistance value will be high. So by connecting the galvanometer from M to N, we choose another intermediate point D in the Kelvin. So that point D will be this one. So D is the intermediate middle point. If the galvanometer deflects to M, then we can say it is showing it is showing less resistance. If it is N, then we will say it is showing high resistance. And the intermediate point here is small d. Okay. So here, this is now the value of resistance that we can calculate. It can be how much? Suppose P and Q, whatever I have written, I have not mentioned the value of P and Q. Suppose P is having, suppose P is having the value of small r1, okay, and Q is having the value of small r2, then easily we can write, if we need to find the value of resistance that can be calculated, that will be r1 by r2, that is equal to P by Q, okay. I hope you understand this equation, P by Q. So this is according to the value of resistance we will use. Now you see here, you know the unknown resistance here is capital R, right? So if we try to modify the equation, then how we can do? And we can again see that P and R are parallel to each other, okay? So we can write the equation like this, R plus small r1, that is equal to P by Q, okay? P by Q multiplied by S plus R2. Can I write this equation? Just check into the device and check the formula, whether I can write this or not. Then you see here, from if I take this as equation 1, this R1 by R2 is equals to P upon Q, then you know what is the value of, now what you have to do, from the where from the 1, you can write again the equation as what? R1 divided by R1 plus R2, okay? R1 plus R2 equals to P divided by P plus Q. Can we write this equation from 1? Because we know that P by Q equals to R1 upon R2. Okay, so again, if we see the position of the resistance in our particular this picture, then we can have this equation. So we can find out R1 from this particular equation. What will be our R1? I can see my R1 is somehow, it will be P divided by P plus Q, okay? P plus Q, and in bracket, I can take it as only R, because R1 plus R2 in a word, I can write this only R, okay? Summation of R1 plus R2 is somehow R, okay? So I can also write like this. So this is my equation, okay, for R1. So I got my R1 value like this. Similarly, you will get, so as I told you, I know that R1 plus R2 is small r. Similarly, you can get your value R2 also like this. So what will be your R2? I'm writing here, okay. R2 will be your somehow Q divided by P plus Q divided by P plus Q. In bracket, you just put it like this, multiplied by R, multiplied by R. So somehow these are the two equations for R, and this is for R1 and this is for R2. So we got two values, R1 and R2. Now we will just put the values, okay, in the required equation, and we can easily find out the value of capital R. How we will do that? I'm moving to the next page, okay. After putting the values, let me tell you how it looks. R plus, okay, in bracket you will put P divided by P plus Q, P divided by P plus Q, I mean the R1 value I'm writing, multiplied by small r, that is equal to P by Q. In bracket you will put S plus what? Q, and divided by P plus Q divided by P plus Q, and here multiplied by R. So this is my value of R1, R2, which I have put here. And after solving this equation, what I can have R equals to P divided by Q multiplied by S. Okay, so this is my equation 2, I can say. And this is my unknown value of R. Okay. So from the above equation, we can say that by connecting the galvanometer at point D means this is the point D, okay? This is the point D. There will be no effect in the measurement of the actual resistance value. But the only disadvantage of this process that it is very difficult to implement, okay? Hence, we use the Kelvin double bridge for getting accurate low resistance value. So this is all about that how we can derive unknown resistance value. So this is a very basic process. Now, this process is complicated one. Okay, so to overcome this process, now we will draw actual Kelvin double bridge. This is a basic process that if someone asks you to find out the unknown resistance, this we can do. But if we try to, now what we will do, as this is a very complicated process, we will move to Kelvin double bridge. Okay, circuit of Kelvin double bridge. So that we will consider. So I'm moving to my PPT once. Wait, let me show you that. So here, see, in the first picture, in my slide, first of all, the same thing which I have did is shown here in separate way, that taking MPN, okay, 3 unknown points, they're trying to find out the unknown resistance here. So it's a bit complicated process. So we will not move with this process. Now we will move on to Kelvin double bridge. So in Kelvin double bridge, you see here is clearly written that it's a 4-terminal resistor having certain terminals and potential terminals. The resistance is defined as that between the potential terminals so that the contact voltage drop at the current terminal do not introduce errors. Now, this is the basic 4-terminal resistor structure of the Kelvin double bridge. Here is shown here. So they have taken, so we will also discuss our Kelvin double bridge taking this kind of picture, this kind of circuit actually. So where you can see here, there are a lot of capital R and small r. Okay, so capital R, R1, R2, R3, and RB, RA have taken small r, R1, R2, R3, R3. Okay, so R1 causes, means small R1, it doesn't cause any effect on the balance condition. And each and every notation here from small r to capital R, they have their own specifications. Okay, so that we will do. Now here in Kelvin double bridge, as you can see here, it's a more specific diagram in this PPT. See here, again, according to the galvanometer, we have taken some unknown resistance, but in some different way, That is here in this construction, it is similar to Wheatstone bridge somehow, but the only difference is that it consists of two arms, separate two arms, which you can say PM and PN. Okay, PM and PN. So that is important, where you can see the connection of galvanometer or between that two separate lines. Okay, so see, from the galvanometer we have these connections, and this connection, actually why we are opting this connection, it minimizes the effect of connecting leads and the unknown resistors, that is R, and definitely the S, which I have shown you in my previous diagram, that can be easily find out from here. So the namings can be different from what I am drawing and what is in this slide. So see, if you know the process, that how we can find out the resistance from Wheatstone bridge or Kelvin bridge, naming you can do anything. Okay, it's up to you, whatever naming you can do. There is no restriction on that. But yes, the process should be same. Okay, so means to finding out the unknown resistance. So for under Kelvin bridge, we will do in the next class. Okay, and definitely we will solve out some problems also on Kelvin. Now up to this Kelvin, do you have any query? Actually, Kelvin, I haven't started in that way. So take down one another problem for your reference that you will do in your home. Take down this problem, very easy problem though. This problem, the galvanometer with the problem which I did in the first, in the beginning of this class, take down that particular circuit diagram. Okay, and this is the problem, example 2. You take it down, solve it at your home and tell me the answer in the next class. Okay, so that is why they have written here. Galvanometer in the previous example now replaced by one with an internal resistance 500 ohm and sensitivity is 1 millimeter microampere, and the deflection of 1 millimeter can be observed on the galvanometer scale. Determine if this new galvanometer is capable of detecting the 5 ohm unbalance in the arm BC. Okay, this is the question, you take it down. And from the previous, the first problem which we did, we need to see that what is my Thevenin voltage, what is my Thevenin resistance, and then you have to apply this problem also in that same circuit. Okay, so in my next class, you will tell me the answer, whatever you have taken out. And this is important. Okay, this particular portion is important because many problems come up from this particular topic. So take it down, then I will once again I'll share the QR code because many students join late. Why you people join late? Huh? और कोई problem हो तो बताओ. Take down this problem, please. Done? You have taken down this problem? Taken down? They respond.
Yes, ma'am.
Then I'm sharing the QR code with you. Again, you just, those who are left with that, they will give the attendance. Respond करने में क्या problem है तुम लोगों को? Huh? You people don't come to classes. Only 14 students are present today.